that's in the past. I can now write my own log. But the important thing is that you shouldn't do that without worrying whether someone else does the same thing at the same time. So you use get-set, which means that you're setting the new timestamp T2, but Redis will return you the old value of that key. And so if the old value returned is T1, which is the same value as you received previously, that means that nobody else set the key in the interim period, and so everything's hunky-dory. If the second process comes along, obviously what happens is that it returns a different value, and that process knows that it did not acquire the lock, and so it should wait and try again at some future point in time. So that's basically what we did, and it's worked great. And we kind of wrote a little abstraction on top of that, which I call a persistent lock, because I wasn't really sure what I should call it. There's probably a better name for it. But the idea is basically an object that keeps reacquiring the lock before it expires. And so effectively the process, when it starts up, if no process is responsible for a given task, it will acquire that lock, and then it will maintain that lock for the entire duration of its kind of existence, until it crashes or someone kills it or whatever. And at that point, another process will come along and pick up that responsibility. So it's quite a nice way, I think, to build kind of these distributed systems. Makes kind of deployment a lot easier. You don't have to worry about responsibility in one place, and it means you can just kind of restart processes at will, really, without worrying who's doing what exactly. So that's the end of that example. Any questions at this stage? I'm probably about halfway through, I think.
So you're saying that you want to avoid a single point of failure. You've got a distributed lock, but isn't your single point of failure now Redis?
Yeah, exactly. I mean, Redis is very reliable, but also
it's reliable as the box is running on.
Well, exactly. And so we end up having a slave Redis instance, and then doing some kind of failover to that slave, which gets a little bit hairy with the locking situation. But I believe it works. In reality, we haven't had a situation where the primary Redis has failed, which is quite encouraging, given that we've been using it in production for about well over a year now. But yeah, you're absolutely right. But the slave Redis should handle that in theory. That's right.
We should chaos monkey it.
Sorry?
Chaos monkey it.
Well, exactly. We should chaos monkey it. Chaos monkey is a great idea. So, yeah. But yeah, good point. I mean, probably the stuff on Redis cluster will help as well. So, I think. So then, next PubSub. So originally we'd used RabbitMQ to do all the message routing for Pusher. So this is routing the actual messages that people are pushing to the API and want routed to all the users. And that worked kind of great in most respects, but our use case was probably quite different to most in that we actually didn't need particularly complex kind of routing topologies, but we had a huge number of bindings. So this is kind of bindings between queues and exchanges, because each client is effectively able to create as many channels as they want with arbitrary channel names. And some people have a habit of creating very large numbers of channels. And if you create very large numbers of channels against RabbitMQ, it doesn't always work out too great. So we were looking for other options, and I must say Redis is basically the reason we switched to Redis was the performance is incredibly good. Just a kind of reference point, I get about 20,000 messages per second on my laptop. That's with about 1 million bindings or pattern or subscriptions, not pattern subscriptions, normal subscriptions. Basically, routing performance seems to be pretty much constant time, which is great for our use case because we don't want to have to control the number of channels that users create. So I was extremely happy with the performance, and then we had a few uses where we needed to kind of do some more kind of advanced routing, which was a little bit complex using RabbitMQ, but actually using Redis PubSub, the combination of subscribe and psubscribe. Is everyone familiar with the Redis PubSub stuff? Okay. So effectively, you can subscribe to a key. So that's just a string key. Any messages that get sent to that key will get sent to you. You can use the psubscribe, the pattern subscribe, to subscribe to a string that contains wildcard operators. And so when a message arrives in Redis, Redis will look for anyone who's got a pattern that matches. So obviously it's a lot slower to use psubscribe, but the nice thing is you can use subscribe and psubscribe in combination. So if you have a few pattern subscriptions, it doesn't kill your performance at all. It's fine. If you've got thousands or tens of thousands of them, then your performance will be bad. And so we're extremely happy. We switched to Redis. It just worked. It's been flawless, and the latencies went down as well, which is great. So then the last example is about synchronizing shared state. So in Pusher we have this thing called the debug console, which when you log into your Pusher account, you can click on the debug tab. You get a real-time list of all the events that are happening in the system, which we quite like because it's kind of meta, because it's using Pusher to be part of Pusher, and it's really useful for people when they're debugging, especially when starting out. It shows you all the messages that are being sent, all the kind of subscriptions that are being made, all the new connections that have been opening from different users and closing, and all the rest of it. So this is quite a handy piece of functionality, but unfortunately, a lot of this data that is shown to the user isn't data that usually gets sent across the message bus or gets distributed in the system. So, for example, sockets opening and sockets closing. Usually that is handled entirely within a given process. So the process handles the fact that a new connection is open from a given app, and it doesn't need to worry all the other processes about that. So when someone opens this debug console, we need to effectively notify all the other users, all the other processes in the system, so that they can start publishing all this extra information that's not otherwise necessary. And so there's kind of two things. The first thing is maintaining a kind of consistent state globally in the system about who's got a debug console open. So that's the first thing. Noting that kind of users obviously can have multiple open in different tabs, and all those tabs will connect to a random socket server within Pusher. There's no kind of optimization of that kind of routing, and so a given process needs to distribute information in order to know whether what happened. So to do that, what we ended up using was sorted sets. Sorted sets. Who's used sorted sets here? Okay, cool. Most people. That's good. I find them extremely flexible for all sorts of things. The idea is basically it's a set that every element in the set has a score, which you can atomically change, increment, decrement, and you can atomically find out all of the elements which have scores in given ranges. So that's kind of great. I've got an example anyway. So you can increment this key consoles, which is going to represent all the debug consoles that are open, by 1 against this application ID. It returns the new value of the new score. You can request the score, so you can use this to check whether that user was active or not. You can, as I said before, you can request the range, and you can decrement, so that's good. So that was kind of a great way of determining that meant that kind of distributed across the system, we knew exactly how many were open at any given point in time. And also, because we get the score in response atomically whenever we decrement, we know that whenever the score goes down to 0, that means the last one was shut. So the idea is that we'd actually like to notify all the processes in the system that this happens, so that they don't have to keep polling against the key and kind of updating their state manually. So pub/sub to the rescue again. It's not only useful for messaging kind of in the traditional sense, but also very useful in terms of just synchronizing state within your system. So what do? We subscribe to some state key. We can just publish to this whenever the state changes, the same as before. So the code is kind of simpler. Just had this in. So if you increment, if the new score is 1, that means that's a fresh user. You need to tell everybody to update their state. Ditto for closing, and then all you have to do is whenever the state changes, you can then request the range for all users that are active and kind of update your list in memory. So this was kind of a great win for us. It meant that from the user point of view, they open the debug console, instantly they're getting all the messages, and kind of like magic. So the atomic operations, again, were great.
How do you get around consistency issues? Say if your application failed in some way and it didn't decrement the counter properly, say number of open consoles, and then it will show up as being open when there aren't actually any open consoles. How do you deal with that kind of situation?
So it ends up being a little bit more tricky. So what we do in that situation is we store kind of, as well as the kind of main information, which is that, we also store the information in so each process in the system has a unique ID, which is assigned from a Redis incrementer. And so we can store against each process the data for just that process. So for a given process application combination, you can store an incrementer. You can store a separate incrementer. And so that means that if a process dies, it's not an automatic operation, but we've got a script so that it will just go through. It uses the keys command so you can select all keys in Redis that match a given pattern. So then you can fetch all of the keys representing processes that have died, and then you can kind of clean up the state. So
I suppose as a last resort, you could reset some keys.
Yeah, that's not ideal because you never really want to take the system offline, so you never really know that the state is 0. So that's a good point.
So do you do any analysis of this? I mean, do you watch in real time what's happening with the number of consoles being used and how they're being used, or any of that sort of?
We don't actually for debug consoles. We could do. I mean, you can look in Redis. Basically, that's the easiest way to see what's going on. You could visualize it, which is how. I mean, in reality, it's a very popular feature for when people are starting out, but then most of our users don't use it very often. So that's one of the reasons it needs to be optimized, so that it's not pushing this information all the time. Yeah. But yeah, we should be, really, given that we're kind of all about real-time messaging, we should definitely be visualizing all this stuff.
Well, I meant in terms of your own uses, that you have some idea of what was going on.
Yeah, absolutely. Yeah, unfortunately, all that kind of thing often falls off the bottom of the backlog, but yeah. I know what you mean. So, I'm pretty much done, actually. I mean, yeah.
So, do you store the data about it, or is it just, it's all ephemeral?
That's all ephemeral, actually.
Yeah, so that's why I really querying.
Right,
so
okay.
Storing the data.
Right, yeah. I mean, we store quite a bit of data, but debug console users is not one of them. Okay. So yeah, just to summarize, I guess. So we're using Redis for really fast lookup, asynchronous, being great to use asynchronously, incrementers for statistics, the distributed locking